Okay, here we are um, with the first of 5 pretty cool videos, and this one deals with chapter 6. So throughout this, I'm going to be asking you questions and then asking you to pause the video, work them out, and then of course I'll solve them. Now, I realize you can just run through this and let me solve everything and go, okay, I get this. Great video, Pullman. But this is kind of like the stuff I'm going to be asking you on the final, and it's worth a lot. So while you're sitting here for these 15 minutes, you should actually do the work. Have a book handy, have your notes handy, and have a row reduced echelon form calculator handy as well, because that makes these things go a lot faster. Okay, so here we go. We're going to start off with two vectors, W1 and W2, which are in R3. Okay, and then we're going to let cap W be the span of W1, W2. Okay, and here's question number 1, Q1. Is the set W1, W2 linearly independent? Prove or disprove. Okay. So here's a moment where, turn off the video and figure out if these things are linearly independent and prove it. So there's 2 ways to do that. The standard way is to say, let C1 and C2 be constants, and let C1 W1 plus C2 W2 equal the 0 vector. And we want to show that C1 and C2 must be 0, or we want to find a relationship between C1 and C2, which would tell me they're linearly dependent. I think these are linearly independent, so I want to show C1 equals C2 equals 0 is the only solution. Okay, so what that amounts to is taking the matrix 2, minus 5, 1, 4, minus 1, 2, multiplying it by C1, C2, and setting that equal to, right? Because this is 3 by 2, this is 2 by 1, so this is going to be 2 by 1, right? 3 by 2, 2 by 1, oops. That should be a 3 by 1. Okay, and so put this guy into an augmented matrix and row reduce it. So let's see here. This is a 3 by 3. Numbers here. 2, not minus 2. 2, 4, 0, minus 5, minus 1, 0. It's easier with a keyboard. And this silly pad. 1, 2, 0. Make sure I don't see any decimal points. done it by hand by now. And there we go. So it's 1100. I guess it picked up the pen mark there. Whatever. So the row reduced echelon form looks like this: 100 010 000. So two pivot columns. Tells me there's no free variables. Hence, W1 and W2 are linearly independent. We also could have shown that W2 is not a multiple of W1, but then you'd have to cite a theorem. Okay. All right, so that was question 1. Question 2. Do the vectors W1 and W2 span R3? Well, we know it spans as W, which is a subspace of R3. Is W equal to R3? No, because the dimension, and here's the full answer. The dimension of R3 is 3. A basis must have 3 vectors, and we only have 2. So the answer is no, because of a dimension argument. Okay. Okay. I have a couple more questions here. I want to show this better, but we'll leave it at that for now. Anyways, that's question 2. Here's question 3. Describe W geometrically. Right, it's not all of R3, so it's not all of space. So it's either going to be what? A plane or a line. And since the 2 vectors are linearly independent, W is a plane. Right, so somewhere on this plane are these 2 vectors, W1, W2. Okay. So, maybe I don't believe you. Here's question 4. Find a vector in R3 that is not a linear combination of W1 and W2. In other words, if I give you a vector and you show me that W1 and W2 produce it, then that vector is in W. And I'm looking for a vector that's not in W, but in R3. This should give you pause to think, well, how do I show that, or how do I find it, without guessing and checking? Because I won't accept that. So, yeah. Prove this. And find me a formula for all of the vectors that aren't in W that are in R3. Or at least some condition. Okay, so what we have here is we have the matrix 2 minus 5 1, 4 minus 1 2, and then we have the span of the column, so the range of this, if you will, actually codomain, and I'm going to let this be A, this be B, and this be C, right? And what I want is I want to find some conditions on A, B, and C, or some subset of them that makes this system inconsistent. Right. Okay, so we flop some rows around here. 1, 2, C, 2, 4, A, minus 5, minus 1, B. That's a 2. Do some row reducing. We get 1, 2, C, 0, 0, A minus 2C, and then we have 5 plus that is 0, 9, and C plus B. Row reduce and swap again, so we have so what do we want? We want A minus 2C to not be equal to 0. And if we choose A and C that way, then we produce a vector that it's not a linear combination of W1 and W2. That's the linear algebra way to do it. I'm teaching Calc 3 right now, so if we want to think about the Calc 3 way, if you take vector W1 and if you take vector W2 and you take their cross product, you get a vector that's definitely not on the plane, so it's in R3 and it's not in W. Cool. So that's two ways to do it, and to do that computation, you got to go back to Calc 3. So what is it? 1, 2 minus, right? 1 minus 5, 2. And where the hell are they? Way up here. 2 minus 5, 1, 4 minus 1, 2. Two minus 5, 1, 4 minus 1, 2. Compute this guy, and I don't know what you get. 9i minus 18k, I think. And so now you have the vector 9, 0 minus 18, something like that. Anyways, you can do that. Okay, so now we've asked how many questions? Four questions. Okay, so now we're on to question 5, and we have these two vectors, W1. I keep writing them. I think I'd have them memorized by now. 2 minus 5, 1, and W2 is 4 minus 1, 2. Are these orthogonal? Let's see. We have 8 plus 5 plus 2. So the dot product is 15. 8 plus 5 plus 2. Yeah. So they're not orthogonal. And we want to produce an orthogonal basis for W. So again, pause this sucker and ask yourself, how do I produce an orthogonal basis for any subspace or vector space for that matter? And what should come flying into your mind is Gram-Schmidt. So we're going to let, following the Gram-Schmidt algorithm, we're going to let U1 be W1, which is 2 minus 5, 1. Okay? And that's one of the two vectors in the basis, or orthogonal basis for W. Okay? And now we're going to find U2. And U2 turns out to be W2 minus, let's see here, W2 dotted with U1 over U1 dotted with itself, U1. Okay. So this becomes 4 minus 1, 2 minus, we dotted W2 with itself up here, so we got 15. U1 is 4 plus 25 plus 1, that's 30. Times 2 minus 5, 1. So this becomes 4 minus 1, 2 minus, so this is 1/2, so 1 minus 5/2, 1/2. So 4 minus 1 is 3. This is 3/2. And this is 3/2. Sweet. So now we have vector number 2, U2. So U1, rewriting this, is 2 minus 5, 1. And U2 is 3, 3/2, 3/2. And let's check the dot product here. It's 3 times 2 is 6 minus 15/2 plus 3/2. And that is 6 minus 12/2, which is 0. So there we go. And we've produced an orthogonal basis for W. And if we wanted to make it orthonormal, which is a hypothesis for many of our theorems, and definitions, if we want to make this orthonormal, what's left to do? We just need to normalize these. So just take U1 over the length of U1 and U2 over the length of U2. I'll let you do that. Okay. And so yeah, that's a series of questions from chapter 6. It's also a lot of stuff from the earlier chapters as well. All of these lead into each other, so it'd be hard pressed to just have one topic all by itself sitting out in space. So and hopefully that wasn't too hard. And yeah, you'll have another one of these on Monday over chapter 5.